Hello everyone, in this video let's talk about redox. So redox reactions are defined as the oxidation reduction reactions. So redox is kind of like the short form for saying both of these reactions together because they both occur at the same time in a reaction. So redox reactions occur whenever there is a change in the oxidation states. So oxidation state is simply the charge on an atom, and the charge, as we know, changes whenever there's a gain or loss of electrons. So we can say that redox reactions depend on the gaining or losing of electrons, because that is going to change the oxidation state, which indicates that we have a redox reaction going on. So now that we are talking about oxidation states, this is kind of the backbone or the foundation of the redox unit. So let's make sure that we all understand how to determine the oxidation states. So we can technically look at the periodic table where we are given the oxidation states in the upper right hand corner. So for magnesium, it's going to be +2. But then the problem is with elements like this, with iron, where we have two possible oxidation states. So iron is an example of transition metals that can have more than one oxidation state. So for something like this, we're going to have to use the math to figure out the oxidation states. Okay, so let's look at magnesium sulfate, MgSO4 for now. Okay, so let's see how can we figure out the charge of the three elements in magnesium sulfate. So for magnesium, as we can see in the periodic table, the charge is +2. So we can go ahead and write the charge of +2 for magnesium. And then for sulfur, we can kind of have more than one oxidation states. So we'll set that equal to X for now. And then for oxygen, the charge is going to be -2. Okay, so when we do the math, we can go ahead and set this equal to, make an equation for this, but we have to take into account the subscripts of each atom. Or in other words, maybe I should say the number of atoms of each element that we have. So for magnesium, we only have one atom, and the charge for that one atom is +2. Plus, for sulfur, we only have one atom, and the charge for that is X. We don't know that yet. And then for oxygen, we have 4 atoms, and the charge for one of them is -2. And then we are going to make an equation out of this. And because this is a neutral compound, we don't see any charge for the entire compound. So we'll just set this equal to a 0. Okay, so then let's just do the math. We basically have +2 plus X minus 8 equals 0. So if we want to solve for X and we are bringing the -8 and the +2 on the other side, it's going to become 8 minus 2. So that's going to be +6. So that means the charge of sulfur, the oxidation state of sulfur in this case, is +6. Okay. So there are some rules that we follow as we are assigning the oxidation states. Make sure that you memorize all of them and you have them on your fingertips, okay? So if we have any element in its elemental form, for example, let's say you are given magnesium as just Mg instead of in a compound, the oxidation state for that is going to be 0. Okay, so here we are looking at a reaction. We see that sodium is in the elemental form, so the oxidation state of sodium is going to be 0. The oxidation state of this chloride is also going to be 0, even though it's Cl2. But remember, Cl2 is diatomic because chlorine occurs in nature as a diatomic element. So this is still an elemental form. So they are both going to have an oxidation state of 0. If we are talking about any monoatomic ions, then their charge is just going to be whatever the charge of the ion is. So sometimes you might be given an equation where you're given an ion in the reactant or the product. So whatever charge you see for that ion is its oxidation state. Number 2, If we are given any metal that is in group 1, the charge of all of the metals from group 1 is always +1. Any metals in group 2 always have an oxidation number of +2. Fluorine is always going to have a charge of -1. And other halogens are also technically -1, especially when they are the most electronegative elements in the compound. So for example, in CaCl2, chlorine is going to be -1 because chlorine is more electronegative than hydrogen. But in HClO, because oxygen is more electronegative, so in that case you have to do the math and solve for X, just like we did in the previous slide. So in that case, chlorine will turn out to be +1. So hydrogen is always going to be +1, except whenever we combine hydrogen with a metal. So when hydrogen is combined with a metal, its oxidation state is going to be -1. So for example, in HF, hydrogen is +1 because fluorine is a non-metal. But when we combine hydrogen with calcium, which is a metal, the oxidation state is going to be -1. Oxygen is always going to be -2, except when it is with fluorine. So in that case, oxygen is going to be +2. So for example, in OF2, it's going to have an oxidation state of +2. And also except when hydrogen is making peroxide. So in that case, its oxidation state is going to be -1. So any type of peroxide. Okay, so lastly, if you talk about the sum of the oxidation states of all of the elements in any compound. So just like we looked at the compound on the previous slide, because the compound was neutral, there was no charge for the compound. So the sum of the oxidation states must be equal to 0. But if we are looking at a polyatomic ion, then the sum of the oxidation states is going to be equal to the charge of that polyatomic ion. So in this case, we are looking at aluminum sulfate because it's a regular neutral compound. So the sum of the charges is going to be equal to, the sum of the charges is going to be equal to 0. However, in case of sulfate ion, the sum of the oxidation states of sulfur and oxygen must be equal to -2. Okay, so let's look at the oxidation reactions, redox reactions, oxidation and reduction in a little bit more detail. So oxidation reaction is when electrons are lost by the substance. And reduction reaction occurs when the electrons are gained. So when the electrons are lost in oxidation, the charge goes up, meaning the oxidation number increases. So think about it this way. Let's say we are starting with 0. When this substance is going to lose electron, it's going to become +1. So the charge goes up when oxidation occurs. In case of reduction, however, if we are starting with 0 and this thing is gaining an electron, the charge becomes -1. So the charge goes down in case of reduction, or we can also say that the oxidation number decreases. So a quick way for us to remember that oxidation, in case of oxidation, electrons are lost. In case of reduction, electrons are gained. We talked about this acronym in class, OIL-RIG. So that means oxidation is loss, reduction is gain. Please do not forget. So, in case of oxidation, whichever species is oxidized is also called the reducing agent, because it's something, a reducing agent is defined as the thing that makes reduction possible. So it makes reduction possible by oxidizing itself. So reduction means gaining of electrons, right? So if this species want the other thing to gain the electrons, it has to lose its electrons first. So reducing agent is, in simple words, the substance that is oxidized. So let's say we are looking at a reaction, and in that reaction sodium is oxidized. So we'll say sodium is oxidized and it is the reducing agent. Reduction is the substance that makes oxidation possible. So this one is also called the oxidizing agent. So based on whichever thing is oxidized or reduced in our in a given reaction, we can write the half reactions. So let's focus on this reaction for now. To first of all, we have to figure out which thing is oxidizing and which thing is reducing, and we do that based on the difference in the oxidation states. So let's first figure out their oxidation states. So magnesium is in the elemental form, so it's going to have an oxidation state of 0. Chlorine is in the elemental form, so that's going to have an oxidation state of 0 as well. Magnesium, in magnesium chloride, magnesium is going to have a charge of +2, so this can come from the periodic table. And then chlorine is going to have a charge of -2. If you want to double check and make sure that the sum of the oxidation states in this thing is equal to 0 because it's a neutral compound, we can do that by saying that we have 1 magnesium and the charge of 1 magnesium is +2, plus we have 2 chlorines and the charge of each one of them is -1. We set that equal to 0, so that's going to be +2 -2, and it is equal to 0. Okay, so then we look at what is happening to each substance. So we see that magnesium is going from a charge of 0 to +2. So 0 to +2 means oxidation number is increasing. It's becoming more positive. That means electrons are lost. So magnesium is oxidizing. So when we write the half reaction, we're going to write magnesium with a charge of 0 and magnesium with a charge of +2. And because electrons are being lost, they are going to go on the product side. The reason why we said +2 electrons is because we are going from 0 to +2. So now look at your chlorine. Chlorine is going from a charge of 0 to a charge of -1. Right? So we're talking about one chlorine atom at a time. So that means chlorine is gaining electrons, so it's going to be reduced. Now when we write the half reaction, we are going to write Cl2 with a charge of 0 and then 2Cl with a charge of -. Now please do not feel the temptation to write this as Cl2 -1. Because remember, Cl2 means these two chlorines are bonded to each other. And if they are bonded to each other, they cannot have a charge of -1. So this is wrong in terms of chemistry. So please do not write that. If you want to say that you have 2 chlorine ions, you're going to put that 2 as a coefficient. Do not put that 2 as the subscript. Okay, so because we have 2 chlorines, we are going to gain 2 electrons. So because the electrons are gained, they are going to be written on the reactant side. So that's what the next thing is saying. Electrons on the product side for oxidation, in the reactant side for reduction. And super important thing that you notice here is that the number of electrons that are lost must be equal to the number of electrons that are gained. Okay, so if we are losing 2 electrons in oxidation, we should be gaining 2 electrons in reduction. If after you write your half reactions, you notice that this is not happening, that means you need to balance your half reactions. But I'm going to talk about the quick little trick that we also talked about in class, which can save us from that situation. So the trick is, if we talk about the rules for writing half reactions, your first step should always be, before you do anything else, before you write your oxidation states, before you separate your oxidation and reduction reactions, your first step should always be to go ahead and balance your reaction equation. So if this is the reaction equation that we are looking at, let's go ahead. So let's balance this equation. So we see that we have 2 fluorines on the reactant side and only 1 in the product side. So let's go ahead and put a 2 with that fluorine. And then we see 1 carbon on both sides right now. We see 3 oxygens here, 1 over here. Now the problem is, if we go ahead and put a 2 there, that's going to change the number of carbons. So we change the number of carbons here again. So that changes the oxygen again. So maybe let's try a 3. So what if I go ahead and make this a 3. So if, because we have 3 carbons there, we can put 3 carbons here. So now let's count our oxygens. So we have 3 oxygens on the reactant side, and we have 3 oxygens in, sorry, 6 oxygens on the reactant side, and we have 6 oxygens on the product side. So that is perfect. Let me erase this thing at the bottom. All right, so this is our balanced chemical equation. So let's move on to the next step, which would be to assign the oxidation numbers to each element on both sides of the reaction. So let's start with iron oxide. So in this case, your assigning the charge is going to be very easy because we can just do the anti-crisscross to bring the subscripts up to become the charge. So iron is going to have a charge of +3 and oxygen is going to get a charge of -2. In copper oxide, we can technically do the same thing. However, what's going to happen here is that carbon gets a charge of +1 and oxygen gets a charge of -1. So the problem here would be that oxygen does not have a charge of -1. It's supposed to be -2. So if we are making this a -2, we are going to have to make carbon a +2 as well, because both of them have the same ratio. Iron in the products is in the elemental form, so that's going to have a subscript of 0. And then for carbon dioxide, it looks like, once again, if we do the anti-crisscross, carbon gets a charge of +2 and oxygen gets a charge of -1. But then again, we want oxygen to be -2 because it should be -2. So if oxygen is -2, carbon should be +4 in this case. So now that we have assigned the oxidation numbers, our next step will be to identify which thing is oxidizing and which thing is reducing. So that's step number 3. So what we notice here, and once we do that, we can just go ahead, write out the balanced reactions and, write out the half reactions and then balance them. So in this case, what we notice is that iron is going from a charge of +3 to a charge of 0. So let me go ahead and write out iron. So we have iron charge of +3 going to iron with a charge of 0. Now the point of balancing this reaction first is so that when we separate them in half reactions, we can take into account the number of atoms that we have for each thing. So I'm going to write 2 ions of iron here, and I'm going to write 2 iron atoms on the product side. So if we are going from +3 to 0, this thing was very, very positive before, but now it's becoming less positive. In other words, the oxidation number is going down. So this indicates that iron is reducing. So that means iron is gaining electrons. So if it is gaining electrons, we're going to have to write our electrons on the reactant side. But how many? So remember that one iron atom is going from +3 to 0, so that means it's gaining 3 electrons. But if you have 2 iron atoms, they are going to be gaining 6 electrons. Okay, so this was your reduction half reaction. So let's see what else is changing. Oxygen, we see that is staying the same because it's -2 everywhere, so nothing's happening to oxygen. But we notice that carbon is going from +2 to +4. So here we have 3 carbons on the reactant side with a charge of +2, and they are becoming 3 carbons in the product side with a charge of +4. So the oxidation number of carbon is increasing. It's going from +2 to +4. That means carbon is losing electrons. So we are going to write those electrons on the product side. But then how many? So one carbon atom seems to be losing 2 electrons, and because we have 3 carbon atoms in total, so 2 times 3, that's going to be 6 electrons that are lost. So as you can see, the number of electrons lost and gained is the same. So balancing the equation at the beginning is really, really going to save your life. So we said carbon is oxidizing. So there you have it, your two half reactions, oxidation half reaction and reduction half reaction. So next up, let's talk about how can we identify redox reactions, because sometimes you might be given a set of reactions and you'll be asked which one is a redox reaction. So the first thing that you can do is assign oxidation numbers to both sides and see if the oxidation numbers are changing. If they do change, then that means there is a loss or gain of electrons. So that indicates a redox reaction. However, this thing can be a little tedious, a little time consuming. So we do have some helpful hints to kind of get you to the answer faster. The first link is that if you see a synthesis, decomposition, or a single replacement, those three types of reactions are always redox. And the reason for that is because in synthesis, decomposition, and single replacement, you always have elemental form of any substance on one side of the reaction, but you have the same substance in a compound on the other side. So, for example, in synthesis, you have maybe two elements combining to make a compound. So, when they are going from element form to the compound form, their oxidation number is definitely going to change, because everything in the elemental form is going to have an oxidation state of 0. But when they become a compound, oxidation state changes. So that is like a very, very quick hint to get you to the correct answer. Okay, so electrochemistry is the application of the redox reaction. So this is where we see or we use the oxidation reduction reaction. So energy is produced using the redox reactions. And there we do that in two different ways. So either by using the voltaic cells, which are also called electrochemical, chemical, galvanic. All three of them are like different names for the voltaic cell. So these type of cells use the chemical energy and they produce electrical energy. So voltaic cells are basically our batteries. And then they are spontaneous reactions, meaning they do not need any external power source. So these reactions, if you just combine the reactants, the reaction is going to occur spontaneously on its own. And then the second way that we use redox reactions is in electrolytic cells. So electrolytic cells actually use electrical energy and they produce chemical energy. So they need a battery or an electrical source to produce chemical energy. So these type of reactions, because we are providing the energy in the form of electricity, they are non-spontaneous. So in all types of electrolytic cells, we are trying to do the reactions that need a lot of energy, or the reactions that do not occur naturally on their own. So because we have mentioned the word spontaneous a lot, so let's do a very quick review of how do we determine if a reaction is going to occur spontaneously or not. So remember, we can use table J. So here's your table J, and using table J, we compare the activities or the reactivities of different substances. So for any given substance, the neutral substance, meaning the one that's in the elemental form, must be more active than the metal that is in the compound, because the metal in the elemental form is supposed to replace the one that's in the compound. So if the one that is in the elemental form or in the neutral form is more active, that means it is going to replace the one that is in the compound. If it's less active, then the reaction will be non-spontaneous. So in this case, we see that zinc is in the elemental form, or it's in the neutral form, because it has the oxidation state of 0, and it looks like zinc is trying to replace copper, because copper, as it has the charge, that means copper is in a compound over here. So We compare zinc and copper in the table and notice that zinc is above copper, meaning zinc is more active than copper. So zinc can replace copper, so this is going to be a spontaneous reaction. But if you compare copper and magnesium, magnesium is much higher than copper, and copper in the elemental form cannot replace magnesium. So this will be a non-spontaneous reaction. It's going to need a lot of energy, which is what we do in the electrolytic cell by using a battery. So naturally, the electrons are going to go from the more active metal to the less active metal. So this is the information that we need for the voltaic cell, because spontaneous reactions occur in the voltaic cells. All right, so let's talk about the voltaic cells. Remember, these are the different names that we can use for voltaic cell. This is the quick setup for a voltaic cell. So we have two chambers, and then the two chambers are connected by a salt bridge. So the purpose of the salt bridge, remember, this is a very important question. There is at least a 90% chance this question is going to show up, so just copy the exact terminology, okay? And please do not get this one wrong. So the purpose of the salt bridge is to neutralize the solutions, and that is done by kind of facilitating the mobility of the ions. So the ions, when the ions are able to move freely in the solutions, we do need that for the voltaic cell to function properly. So the salt bridge helps with the mobility of those ions, and it neutralizes the solutions. So then we have one of our chambers is going to act as the anode, or the negative side of the cell, and that's because the reason why we call this the negative side is because it's on the negative side of the salt bridge. So super important concept, and this is what most people get confused about, the kind of the cathode and anode for voltaic and electrolytic cells. So in the voltaic cell, your anode is the negative side because it's on the negative side of the salt bridge, and your cathode is the positive side because it's on the positive side of the salt bridge. So as you can see, the anode is getting the nitrate ions, the negatively charged nitrate ions, and the cathode is getting the positively charged sodium ions from the salt bridge, okay? So then, why is it stuck? Okay, so because this is a spontaneous reaction, that means electrons are going to flow from the more active metal to the less active metal. So this is a cell between zinc and copper. So zinc is more active. That means electrons are going to flow from the zinc electrode to the copper electrode. So when that happens, the zinc is losing electrons. So zinc in the elemental form, or the neutral state, when it loses electrons, that means oxidation occurs at the anode. And the Zn positive 2 ions, so as the zinc is losing its electrons, the cations, zinc cations that are left on the electrode, they are going to break into the solution, as you can see here. So as they break into the solution kind of becomes more positively charged. And so eventually what's going to happen is that the mass of the zinc electrode is going to decrease, because remember, the electrode is losing electrons and it's also losing the zinc ions. So as the electrode keeps losing more electrons and more zinc ions, the mass of the electrode is eventually going to decrease, and the ion concentration in the solution is going to increase. So there are going to be more and more ions in the solution. Okay, so this is what your half reaction is going to look like on the zinc electrode, because it's oxidizing. So we are saying that each zinc metal is converting into, or one zinc atom is converting into a zinc ion and losing 2 electrons. So the thing to remember here is that at the anode, oxidation is occurring. So the acronym that we discussed that you can use to remember this is ANOX, meaning anode, oxidation. So here we decrease the mass of the electrode And then we also decrease the number of electrons because we are losing electrons. On the other side, copper is gaining electrons, so that's where reduction occurs. And the copper ions that are in the solution, so this solution has copper ions already, so maybe it's like copper sulfate solution or whatever. It could be just any solution that has the copper ions already. So the electrode is getting the electrons, and these electrons are pulling the copper ions from the solution, so they are now going to get deposited on the electrode. So eventually what's going to happen is that the mass of the electrode is going to increase, because remember, this one is gaining both the electrons and it's also gaining the copper ions from the solution. So the ion concentration in the solution, however, eventually is going to decrease because we are pulling those ions or attracting the copper ions from the solution. So this is what the half reaction at the cathode is going to look like. So the key thing to remember here is that reduction occurs at the cathode, and the acronym that we talked about to remember this is REDCAT, reduction at the cathode. So eventually the mass of the cathode increases, and so does the number of electrons, because cathode is gaining electrons. So that was your voltaic cell. Now let's talk about the electrolytic cell so that we can compare both of them. At the electrolytic cell, we have non-spontaneous reaction, and we need electrical energy to convert that into chemical energy. So whenever you see a battery present, that kind of identifies the that we are looking at an electrolytic cell, because we are using electrical energy. So in the other than battery, the other things that make it different from voltaic cell are that there's only one reaction chamber and there's no salt bridge. So one of the applications of an electrolytic cell is electrolysis. So this is when we can separate a compound into its elements using an electrolytic cell. So this diagram that you see on the screen right now, this is an electrolysis reaction occurring. So and it's just the electrolysis of water, let's say. So the water is breaking down into hydrogen and oxygen. So your anode in this case is positive and the cathode is negative. So notice that this is now the opposite of what we had in the voltaic cell, and that's because in this case, in the voltaic cell, the positive and negativeness of the anode and cathode depended on the salt bridge. In this case, the positive and negative depends on what side of the battery is the electrode on. So the anode is always on the positive side of the battery, so that's why it's positive. And the cathode is always on the negative side of the battery, so that's why it's negative. Okay? And so what's going to happen is at the anode, we always have oxidation occurring, meaning there's going to be loss of electrons. And then at the cathode, we are going to have reduction occurring, meaning there will be the gain of electrons. So the electrode is going to lose electrons, and then the anode is going to lose electrons, and the cathode is going to gain electrons. Okay, so if we can still use the same acronyms, NOx, REDCAT, if we talk about the half reactions that are occurring at both of them. So at the anode, we have oxygen, which is losing electrons. So we are going from O2 minus to oxygen in the elemental form, and it's going to lose its electrons. So we got the O2 minus, by the way, from this reaction equation at the top. So the two products are in the elemental form of 0, and then hydrogen has the charge of +1, oxygen has the charge of -2. Okay, so oxygen is going from -2 to 0, and it is losing 2 electrons. We should write 2 oxygens here, by the way, because we have 2 oxygens on the reactant side. And then here we should write 4 hydrogen ions instead of 2 hydrogen ions. So 4 hydrogen ions, they are together, they are gaining 4 electrons and converting into 2H2. So the other half reaction that was given here before, that was just not balanced. So same thing, if we come back to the oxidation half reaction, once again, I did not balance the equation. So when we are balancing this, remember one oxygen atom is losing 2 electrons, so 2 of them are going to lose 4 electrons. So now it's balanced. Alrighty. So this is what electrolysis is going to look like. It's basically just breaking down or separating a compound into its elements. We still have N-ox and red cat, meaning oxidation at the anode and reduction at the cathode. And remember that this is an electrolytic cell, so anode is positive because it's on the positive side of the battery, and cathode is negative because it's on the negative side of the battery. Okay. So let's look at the other way in which we can use an electrolytic cell, and that is electroplating. So electroplating is when we are coating an object with an element or a metal. So in this case, the example that you see on the screen, we are trying to coat a spoon with silver. So the electrode, our anode that we see, is the silver electrode, and then our cathode is the spoon. So at the anode, we see that the anode is losing electrons. That means oxidation is occurring here, and so as it's losing the electrons, it's also losing the sodium ions into the solution. So this is what the equation is going to look like for the oxidation reaction. So the silver in the solid form is converting into silver ion, and it's also losing the electrons. So the cathode is going to be gaining the electrons, and once it gains the electrons, this electron that we have on the spoon is going to attract the silver ions that are in the solution. So those silver ions are going to get deposited on the cathode. So this is how we coat the silver on the spoon, because the electrons on the spoon are going to attract the silver ions. The ions and the electron combine, they make the metal or the atom, and that atom gets deposited on the spoon. So this is what the reduction half reaction is going to look like. Nothing is happening to whatever the spoon is made of. So whether your spoon is made of silver, whether it's made of something else, maybe iron or whatever, nothing is happening to that substance. The silver is what is reducing at the cathode as well. So silver is gaining electrons there and converting into silver atom. So one very, very quick kind of hint to always remember about electroplating is that whatever substance is being coated is always going to be the cathode, because that substance is always the place where reduction is going to occur. So that's the one that is going to gain electrons, and then it's going to attract the ions from the solution so that ion or the new atom can get coated on top of it. So whatever you are coating is always going to be the ion. And then whatever metal we are using to do the coating, that is always going to be your anode, and it's going to be attached to the positive side of the battery. So just like what we said in electrolysis, in any type of electrolytic cell in general, anode is positive because it's on the positive side of the battery, and cathode is negative because it's on the negative side of the battery. So anox and red cat is still true for electroplating as well, because we have oxidation occurring at the anode and we have reduction occurring at the cathode. So let's go ahead and compare voltaic and electrolytic one last time. So some similarities between both of them is that they both have our applications of redox reactions, meaning there is gain or loss of electrons going on, and then both of them have oxidation occurring at the anode, and they have reduction occurring at the cathode. So anox, red cat. This is the same for both type of cells. So then what are some differences? In voltaic cell, we have spontaneous reactions. In electrolytic cells, however, they are non-spontaneous reactions, so they need energy to happen. So that's why voltaic cell is the battery, because it's producing electrical energy. But okay, so because they are spontaneous, so the electrons go from the more active metal to the less active metal. We can always use table J to figure out which metal is more active. In case of electrolytic cells, they are going to need a battery, and the reason why we need the battery or the energy source is because we are trying to force the electrons to go in a certain direction, even if it's not what we predicted according to table J. So because this is where non-spontaneous reactions occur, right? So we are using that energy to force the electrons to go in our desired direction. So in case of spontaneous reactions, we have two reaction chambers and a salt bridge, only one chamber and no salt bridge in case of electrolytic. So in case of voltaic cell, the anode is negative because it receives negative ions from the salt bridge, and the cathode is positive because it receives positive ions from the salt bridge. Comparatively, in electrolytic cell, the anode is positive because it's connected to the positive side of the battery, and then the cathode is negative because it's connected to the negative side of the battery. So that was it for the redox. I'll see you in the next one.